What's going on, everybody? Jake here, coming at you with another math lesson today. Coming at you live again, kicking off the winter term or spring semester, depending on how your school does it, with another Monday night live stream. We're doing these every Monday night at 5 Pacific, 8 Eastern, so be sure to join us each week and get whatever questions you have answered. I always like to, have some time at the end for live Q&A. So whatever questions you have along the way, feel free to drop them in the comments or the live chat, and I'll be sure to answer as many questions as I possibly can. If you're getting some use out of this, please be sure to hit that like button as well. But let's go ahead and jump into it. I got a couple different problems I wanted to go over with you today. One is going to be in the derivative side of calculus, and the other is going to be on the integral side of calculus. So whether you're starting off a new term in calculus 1 or kind of continuing on, should have something helpful for you today. I did also drop a few links in the live chat for a couple things that I have that might be helpful to you as well. Study guides and Calculus 1 package that I offer as well. So be sure to check out those links too. But let's go ahead and jump on into the first example here. So we're going to start out with an implicit differentiation problem. Part of this problem actually was left as a comment on one of my videos that a viewer was asking me to solve. So just a good reminder for you, ask whatever questions you want on my videos, comments, live chat, posts, whatever the case is. I always try to help answer whatever questions I can. So in this case, we're going to be finding dy dx by implicit differentiation. And the problem that we're going to be starting with, or the problem we're given, is x to the fifth times y to the fifth equals y plus x. So generally these implicit differentiation problems, whenever you're trying to find dy dx, or really d anything over d anything, they're going to follow the same process, the same few-step process. So the first thing we want to do when we're looking at an implicit differentiation problem like this is, first of all, look at this right here. Look at what it's asking us to find. It's asking us in this case to find dy over dx. Well, this one little thing right here actually gives us a lot of information about what we're trying to find and how to actually get there, how to find it. So right off the bat, just by looking at, like I said, d anything over d anything, whatever you have on the top here, in this case y, that right there tells you right off the bat, we want to treat y as a function. So y is a function, and the thing that it is a function of, there we go, is going to be whatever this letter down here is. So right here we know x is going to be our variable. X is the variable. So right away we know y is a function of x. So you could almost think of it like this, y of x. Well, really all this is to say is when we're taking the derivative with respect to our variable, so we're always going to take d whatever this bottom thing is, in this case d dx, of both sides of our equation. When we're doing this, whenever we see an x, we can treat that as our variable. We can take the derivative of things that only have x's in them, just like you know how to take the derivative of anything, right? But where it gets a little weird, where you have to kind of apply the chain rule, basically, where you have to apply this kind of special implicit differentiation step, is whenever you have something with y in it. So basically, as we look through this equation, both sides of our equation here, we kind of have three main terms. X to the fifth, y to the fifth is one term, y is one term, and x is one term. When I say term, I mean anything being kind of multiplied together is going to be one term. If we have a plus or a minus, that's a separate term. So y plus x is two separate terms, where x to the fifth times y to the fifth is all one term. This term here and this term here, since they both have y's in them, we're going to have to apply the chain rule when we take d dx of both sides of our equation. But this term here, since it only has an x, we're going to be able to take the derivative of that as you would expect to be able to take the derivative of that. So all that really means is whenever we go through each of these terms and take the derivative of them kind of on their own, whatever has a y in it, we're going to have to treat a little bit differently. So when we're taking the derivative, we'll start on the left side of our equation here with x to the fifth times y to the fifth. Well, that's a product. We have the product of these two separate things here. So we're going to have to use product rule, actually. So when we're taking the derivative using product rule, we want to kind of break this down into f and g. So in this case, we'll just say f is going to be this first part, x to the fifth, and g is going to be this second part, y to the fifth. Then we're going to have to find f prime and g prime in order to apply the product rule formula. And this product rule formula is one of the formulas covered on my free Calculus 1 study guide. I did drop a live chat with the link to that. You can also look down below in the description of the video, and you can get a link to that study guide as well. It is free, available for instant download, and this formula is on there. But to take the derivative, or to take f prime, what we need to do is just take the derivative of this f term, which, since this only has an x in it, and we're taking the derivative with respect to x, since we're taking d dx, this one little piece only has x's, we can just use the power rule. The derivative is going to behave the way we would expect it to. So we're going to bring this 5 down in front, bring the power down in front, keep our base x as x, and then lower the power by 1. 5 minus 1 is 4. Now for taking g prime here, we're going to have to do something a little bit different, because now, keep in mind, we're taking d dx, which means we're taking the derivative with respect to x, and this has a y in it, which y is a function of x. So as a result, we have to use chain rule. What we basically want to do is treat this as we're taking some function of x, which is all being raised up to the fifth power. So chain rule says we have a function within a function. We have to use the chain rule. Well, the chain rule is just going to be taking the derivative of the outside part, so moving the 5 down in front, keeping the inside the same, keeping our y as y, that's not going to change, lower the power by 1, so make it a 4, and then by the chain rule, we need to multiply this by the derivative of our inside function. Well, the derivative of y is a little bit weird because we don't really know what y is. That's why we're doing implicit differentiation in the first place. If we knew what the function y was, we could just take its derivative, not implicitly, just explicitly take the derivative, basically. But since we don't know what y is, we can't know what y prime is, or what the derivative of y is. So instead, what we can do is just say the derivative of y with respect to x is just dy dx, which, you know, this notation literally just means the derivative of y with respect to x. So this is going to be our g prime now. Let me get this out of here real quick. All right, so now to apply the product rule, what we need to do is basically multiply this f times g prime, multiply the g times f prime, and then add those two things together. So we will do 5y to the fourth dy dx times x to the fifth, which gives us 5x to the fifth y to the fourth dy dx. And then we're going to add 5x to the fourth times y to the fifth. Okay, so that is the derivative of the left side of our equation. Now for the derivative of the right side of our equation, we have y plus x. Well, we can just take the derivative of each of these two terms separately, since it's just the sum. The derivative of the sum is the same as the sum of the derivatives, which also is on my free Calculus 1 study guide I mentioned, linked down in the description. But what we're going to do is, I just realized I'm kind of cutting that off there. There we go. We can take the derivative of these two terms separately. So we're going to have the derivative of y, which, like I just said, if we don't know what y is, we don't know what the derivative of y is. But we do know, since we're taking the derivative with respect to x of y, that's just going to be dy dx. Then the derivative of x, since that only has x's in it, it does not have a y in it, the derivative is going to behave the way we would expect, because we're taking the derivative with respect to the thing that we're taking the derivative of. So the derivative of x is just going to be 1. So now the next step in any of these implicit differentiation problems is going to be to basically add or subtract all of our dy dx terms over to one side of the equation add or subtract all of our non-dy dx terms to the other side, and then we'll kind of go from there. So first of all, we can see we have a few terms here. We have one term there plus another term there, one term here plus one term here. So what we're going to want to do is think about which terms have dy dx and add or subtract them all to one side of the equation. Doesn't really matter which. I'm just going to go ahead and move them all to the left. So this dy dx term is already on the left. This non-dy dx term needs to move over to the right then. So we'll subtract 5x to the fourth, y to the fifth from both sides of our equation. Whatever you do to one side, you have to do to the other side also. And then we have a dy dx term over here, which we want to subtract from both sides of our equation, so that we cancel this one from the left side, we cancel this term from the right side, and then what we are left with is this 5x to the fifth, y to the fourth, dy dx, minus the dy dx from the right side, and then equals this 1 that was over here on the right before, minus 5x to the fourth times y to the fifth. So now that we've got all of our dy dx terms on one side, all of our non-dy dx terms on the other side, what we can do is factor out the dy dx terms from the left side of the equation, or factor out the dy dx itself. Because what this is going to do is it's going to leave each of these terms within the parentheses here, but without the dy dx part of it. And the reason why that's really nice is because now we have an equation that only has one single dy dx, which is the thing we're trying to solve for. So it's much easier to solve for something when you only have one of it. So when you can kind of add or subtract everything containing that thing that you're trying to solve for to one side of the equation and then factor it out, it reduces it to a single thing, which makes it a whole lot easier. And that's a pretty good strategy with any sort of problem that you're trying to solve for something, not just implicit differentiation. If you're ever trying to solve for a specific variable, that's another really common kind of helpful strategy that can be used in cases like that too. So now once we've got our dy dx factored out, we can divide both sides by everything within the parentheses here. So doing that is going to divide both sides by this. It's going to cancel on the left. And we're going to be left with dy dx equals 1 minus 5x to the fourth, y to the fifth, over 5x to the fifth, y to the fourth, minus 1. So that is how you solve for dy dx in that case. I'm not seeing any questions here, so we'll go ahead and jump on to the next problem I have here. Which we'll just scroll on over here. All right. So I wanted to do an integral type of problem as well, since it is the start of the next term for a lot of people out there. And many of you may be starting Calculus 2 or integral calculus at this point. And this is kind of one of the first things that you're probably going to be getting into. So like I said at the beginning of the video, if you do have any questions along the way, whether they're related to what I'm doing or not, feel free to drop any questions you have in the live chat. I'll do my best to answer whatever questions you have live at the end here after this problem. So what we're going to be doing is we're going to estimate the area under the graph of f of x equals square root of x from x equals 0 to x equals 4 using 4 approximating rectangles and right endpoints. Then we're going to sketch the graph of the rectangles and figure out if our estimate is an underestimate or an overestimate. So really when you're doing any of these types of problems where you're trying to estimate the area under the graph of a function using whether it's the left endpoints, the right endpoints, or the center point, those are all three cases that you're probably going to have to deal with. There's really just a formula that you're going to want to use. And these formulas, all three of them, are actually on my Calculus 2 study guide. There's a link down in the description, or in the live chat. I did post the links to that study guide as well. But this is one of the formulas on my Calculus 2 study guide. So this may look a little bit confusing at first, but basically if we're trying to find, or estimate, I should say, this is the right endpoint formula. So if we're trying to estimate the area under some function f of x between two x values, a and b, we can estimate it using this sum, this sigma notation, which is to basically take the sum from I equals 1 to n of f of x sub I times delta x, where your delta x is just your b minus a over n. So b is just the right endpoint of the area. A is the left edge of the area. So in this case, if we're trying to estimate the area from x equals 0 to x equals 4, we're going to have b equaling 4 and a equaling 0. And then we also know that we're doing it using 4 approximating rectangles. So n is the number of rectangles that you're using. So in this case, our n is going to be 4. So basically what we can do is we can find our delta x, which is just b minus a, so 4 minus 0 all over 4, which is going to be 4 over 4, which is 1. So our delta x is going to be 1. And then our x sub I, we could figure out each, or what we need to do, I should say, is figure out each of our x sub i's. So their kind of general formula for x sub I is just your left point, so our a, so 0, plus I times delta x, which is 1. So basically, in this case, our x sub I is just going to be I. Well, what that means is we're going to start at our first x value, which we are going to go from, like this sigma says here, we're going to go from I equals 1 up to n, which is just the number of rectangles we have. So in this case, we're going to go from I equals 1 to 4. And we're going to plug in our I into this equation that we just got for x sub I and figure out all of our x values. Well, if we start at x equals 1, or I'm sorry, if we start at I equals 1, that's going to be, we already know, our first x value, because x sub I, or in other words, x sub 1, is just going to be I. It's just going to be 1. Then our second x value, we would just take I equals 2, plug in that into this equation that we just got here to get x sub 2 equals 2. And then we would do that again for I equals 3 and I equals 4, which is as high as we're going, because remember, this formula says we only go up to n equals, or we only go up to I equals n, which is the number of rectangles, which in this problem we have 4 rectangles. So we're going to go up to I equals 4, just plugging the I into this equation that we found of x sub I equals a plus I times delta x, which is just x sub I equals I, x sub 3 equals 3, x sub 4 equals 4. So basically we have these 4 x values, okay? Now, once you've found those 4 x values, you can see the kind of sum equation that we have here. What it's basically saying is we're going to take the sum from I equals 1 to n of f of each of our x values times delta x. So in this case, we're taking the sum of f of our first x value, which is 1, times delta x, which is 1, plus f of our second x value, which is 2, times delta x, which is 1. And then we would do that again also for our next 2 x values. Kind of running out of room here. Let me scroll over. Plus f of 4 times 1. So basically, in this case, what we've done is we've kind of, reworked or simplified this formula, which would approximate the area under this function. We've broken it down into these 4 terms, which if we can figure out what these 4 terms are, and then sum them up or add them together, that will give us the approximate area under that curve based on our right endpoint area or our right endpoint formula. Or I guess I should say using the approximating rectangles based on the right endpoint of each of those rectangles. So what we need to do then is figure out f of 1, f of 2, f of 3, and f of 4. Well, to do that, all we would do is take 1, plug it into our function f of x, which, remember, the function that we were given, the f of x that we're trying to estimate the area under, is the square root of x. So we're just going to plug in 1, 2, 3, and 4 into our f of x equals square root of x. So f of 1 is just the square root of 1. F of 2 is the square root of 2. F of 3 is the square root of 3. And f of 4 equals the square root of 4. Square root of 1 is 1. Square root of 2 and square root of 3 we'll just leave in exact form for now. And then the square root of 2, or the square root of 4, is 2. So basically what we can do now is plug each of these 4 numbers back up into this thing here, where we have f of 1 times 1, which is just f of 1, which is 1. F of 2 times 1 is just f of 2, which is the square root of 2. F of 3 times 1 is just f of 3, which is root 3. And then f of 4 times 1 is just f of 4, which is square root of 4, which is 2. So basically, this is going to estimate the area under our curve f of x equals square root of x using the right endpoints and using 4 approximating rectangles. But remember, what we also have to do at this point, well, what you could do if you wanted to is plug this into a calculator to get a decimal approximation. That would be fine for you to go ahead and do that. I'll just go ahead and leave it in exact form. But remember, the question did ask us to do a couple more things here. It asked us to sketch the graph of the rectangles and figure out if we have an underestimate or an overestimate. So let's think about what the graph of this function looks like. So if we think about this function, f of x equals the square root of x, it's going to look something like this. And we are looking at the area from 0 to 4. So basically, we're looking at the area from here to here. So this kind of gives us, you know, the edges or the endpoints of the area that we're trying to estimate. So if we were going to think about the actual area under this curve, it would be this area in here. But remember, what we're doing is we're trying to just estimate using 4 approximating rectangles. Well, since it's based on the right endpoints, basically what that means is the height of our 4 rectangles, they have to line up with our function at the right endpoint. So if we're splitting this from 1 to 4 into 4 rectangles, we're going to split it at each of the whole number spots, right? So if we're thinking about our right endpoints, that's going to be here, 1, 2, 3, and 4, which are exactly the x values that we got by plugging into that formula, right? We got 1, 2, 3, and 4. So what that means is if we kind of extend these endpoints, 1, 2, 3, and 4, up to our function, and then this is going to be the right edge of our rectangle. So our rectangle is just going to then go over to the left edge of this little interval that we're looking at. And then same thing here. We're going to start at our right endpoint, go up to our function, and then our rectangle is just going to go over to the left edge of this little interval, which just goes basically to our previous x value. Then again, we go to our third x value, go up to our function, and then go over to the left edge of this interval, which goes back to our previous x value of 2. And then finally, we have 4 going up to our function, go over to the left edge of this interval, and then down to our previous x value. So that gives us these 4 rectangles. So now just looking at this, we can pretty easily see whether this is an overestimate or an underestimate, because you can see that since it's based on the right endpoint, all 4 of these rectangles, you can see, go up over the top of our function. So you can see kind of this area up here for all 4 of these rectangles is being counted in our rectangle approximation of the area, but none of this is under the curve. None of this would be counted as the actual area under the curve. So these kind of shaded in yellow sections would be contributing too much area to our estimate of the area under this curve. Therefore, we can see that this approximation we got using the 4 rectangles is going to be an overestimation because there's too much area counted in it. All right, so let's see if we got any questions here. I'm not seeing any questions in the live chat. If anybody has any questions, feel free to throw them in the live chat there. Even if they're not related, happy to help try to answer any questions you have. And if you don't have any other questions, feel free to check out those links I dropped in the live chat there. Those same links are in the video description below if you want to check them out there. But got some good resources for you, whether you're taking differential calculus or integral calculus, calculus 1 or calculus 2. Got some study guides and complete calculus 1 package that should be a huge help to you. So go check out those links and hopefully you find something helpful. But I'm not seeing any questions, so we'll go ahead and wrap things up there. If you got some use out of this video, please be sure to hit that like button down below. It really is a huge help to me. It helps YouTube, put this out in front of more people so we can keep growing the Jake's Math Lessons community and get more people in these live streams, start getting more questions, and keep things going. So a like would be very much appreciated. So we'll go ahead and wrap things up. Hope you all have a good rest of your night and a good rest of your week. And catch you next week. Be doing another live stream next Monday night, same time.